This is 3.8, and it's implicit differentiation. So let me maybe start by talking about what is a implicitly defined function. So normally, right, you would write y equals, and then there's some terms with x's, right? So 3x squared plus 3x minus 7. So this would be explicitly defined function. So explicitly defined function. So we have, and y is on one side, on the left side, and x's are on the right side. So implicitly defined function would be something like this. So it would be y plus x equals 3. Alright, so this one is very easy to, alright, so this one is implicitly defined function. So implicitly defined function. And you see that it'll be very easy to change it to explicitly. And of course we in some case, most cases we prefer the explicitly defined function. Right? So something like this. But in some cases, right, it's useful to have a function defined like this, like in this way. Okay, so I'll show you an example where that would be useful. So before, let's look at example 1, and that's something that we've done before. So example 1, and so find derivative at any point on a circle. At any point on the circle. Yeah, we had the circle, and it was defined like this. So x squared plus y squared equals 25. All right, and you see that this is an example of an implicitly defined function, because we don't have y on one side and the rest of the function we don't have y on the left side, and we don't have the rest of the function on the right side. So the way we did it was like this, right? So we solved for y, sorry, and that was a square root of 25 minus x squared. And then we took a derivative of this, and we got, I'm not going to do it, I'm just going to write the solution. Alright, so the solution was something like this. Minus x, and here we have 25 minus x squared. And if we want to find, say, a slope of a tangent line that's tangent to that circle at a certain point, right? We just plug in, like say we want to find the slope of a tangent line at 3, 4. We plugged in 3, right, for x, and we got that slope was m equals negative 3/4. Okay, what I'm doing, I'm just plugging that 3 into that formula for slope, into the derivative. Okay, but the problem is that I can't really, using this type of differentiation, this type of formula, I cannot find a slope so impossible to find derivative Right, so if we try to find the derivative at, say, 3 negative 4, right, we wouldn't be able to do it, because that would give us the same number the same slope as this one, right? And that wouldn't be true, right? That wouldn't work. So we need to have a way to plug in that -4, right? And that's what implicit differentiation will help us with. But before we get there, let me give you a couple simpler examples of that implicit differentiation. So let's say I want to let's say we have a function defined like this. So y equals f of x, and then we have x cubed. Right, so to find the derivative, so that would be dy dx, or d of that particular function, right? So that's 3x squared. Okay, so now if I had a function defined in a slightly different way, so something like this. So I'm taking derivative of, instead of x to the third, this time I have y to the third. Okay, so in a sense, this is a chain rule, so that this is the outside, right, and that y is the inside. Okay, so now I need to take a derivative of the outside, keeping that inside unchanged, just like we're following the rules of the chain rule. So that would be, let me write it in red. So that would be 3y squared, right? So we're treating that y just as a regular variable, 3y squared. But now I need to multiply it by the derivative of the inside. Derivative of the inside is dy dx. Okay, so that would be, right, that's an example of implicit differentiation. Right, so we got derivative of the outside, right, so that's this. And then I need to multiply it by derivative of the inside. Inside is y, so it's just dy dx. And we could, we could take basically we could take any function and change it to implicit functions. So say something simple like this. So y equals 3x plus 4. Okay, so if I'm taking derivative, I'm writing y prime equals, and now I just take derivative of 3x plus 4, so that's just 3. Okay, so let me rewrite that. Right, so this is just a straight line. Rewrite that in implicit form. Okay, so that would be y minus 3x equals 4. So now to take a derivative, right, I would just do it the same way. So derivative of y, right, and just like here, right, this exponent of 1 is the outside. Okay, so I'm just taking this 1, putting it in the front, and then subtracting 1, so this is just 1. Right, I hope you understand why. And now I'm taking derivative of the inside, which is y prime. Okay, now I have 3x, so derivative of that will be negative 3. Derivative of a constant is 0. Okay, so essentially I got the same thing, right? I had to get the same thing, right? So y prime equals 3. So I could treat any function the same way, right? I could solve it for for y and then take a derivative, but sometimes it's impossible, right, to solve for y. And in some cases, right, even though I would solve for y, the formula I would get for slope just wouldn't work for certain numbers,